Okay, so in yesterday's class, we had stopped with the partitional clustering techniques. I hope you remember the three partitional clustering techniques that we had discussed. Okay, so in today's class, we are going to start with the next set of techniques. Okay, so next set of techniques which fall under the category called hierarchical clustering techniques, hierarchical clustering. Okay, so this is the second category of clustering techniques which we are supposed to discuss. Okay, so this actually involves creating clusters that have some sort of ordering, either from the top to bottom or from the bottom to top. Okay, some sort of ordering is there. Okay, so I mean, you can equate it to an analogy of how the files and folders are being stored on the hard disk, how they are being organized on the hard disk as a hierarchy. You can equate it to that. Okay, so there are actually two types of hierarchical clustering. One is what is called the agglomerative clustering, and the second one is what is called the divisive clustering. Agglomerative and divisive. Agglomerative, the short form, Agnes, and divisive, it's Diana technique. Okay, so divisive clustering. So if you see this agglomerative clustering, clustering, so you can see from here. This is step 0, 1, 2, 3. So initially you can see all the individual samples. Okay, so they are considered as a separate cluster. That is, it is considered as a cluster with single elements. Okay, so initially all the elements in the data set at a consideration, it is being considered as a cluster with single element. Then after that they start getting merged. You can see they start getting merged. Okay, so that process continues till you are getting a single large cluster. Okay, so that's what is agglomerative clustering all about. Okay, you start with individual data points as one element in one cluster, then you start merging them. See, you start merging them. Then the process iteratively continues till you land up with a single cluster. Okay, so the divisive clustering is just the opposite of Agnes, your agglomerative clustering. So that starts with all the samples in the data set. So it goes in this direction from right to left. So it starts with all the samples in the cluster initially taken as one single cluster. Then you start partitioning it. Okay, so initially all the samples of the data set is chosen, and then it starts getting partitioned, and the partitioning process will continue till finally the cluster is being split into small clusters. What happened?
Ma'am, is it hierarchical clustering comes under supervised or unsupervised learning?
Unsupervised learning. Clustering as such comes under unsupervised learning. So the entire clustering, whatever be the clustering technique, whether it is for small data set or larger data set, or for spherical shapes or arbitrary shapes, or with noise or without noise, whatever it is, the entire set of clustering comes under unsupervised learning. So this part, as far as the divisive clustering is concerned, so the process continues till you land up with the elements separated out into separate clusters. That is, each cluster having one element. Okay, so agglomerative method is all about merging the clusters. Okay, merging the clusters to reduce the number of clusters. Okay, so that process is repeated each time. So that is what I mean. You start merging two to nearest clusters to get a single cluster. That process proceeds till you get a single cluster, and divisive clustering is the opposite of it. Okay, so now we will just look into what this agglomerative clustering is all about. Okay, so this is agglomerative nesting mentioned here, the person who's introduced it, and you can see here, use the single link method and the dissimilarity matrix. Okay, so let me tell you what that is. Okay, so there are actually uh, different ways to measure the distance between the clusters in order to decide the rules for clustering. Okay, and that's popularly known as linkage methods. After a few slides, I'll show you what are the various linkage measure methods which will help you to measure the distance between the clusters, okay, to finalize the rules for clustering. Okay, so one such method is what is called your single link method. Okay, single link method is the one which is being popularly being used. Okay, so uh, yeah, so the single link method is what is being used in your agglomerative clustering. Okay, so what the single link method, what it tells you is, so this is what is single linkage. Okay, so the distance between two clusters, how it is being defined is the short, how it is being defined is it is considered as the shortest distance between 2 points in each cluster. You can see here. So the shortest distance between 2 points, the shortest distance between the 2 points in two clusters, that's what is called your single linkage. Okay, so this linkage, it can be used to detect let's say high values in your data set. High values in the sense extreme values in your data set. Like extreme values can be actually outliers, okay, because they will finally get merged only at the end. Okay, so there are many other linkage methods too, like complete linkage, average linkage, centroid linkage, and other things. But out here, the agglomerative clustering takes into consideration only the single linkage aspect. Okay, the distance between the two clusters defined as the shortest distance between the points in each cluster. Okay, and again, I just mentioned there are different linkage methods. Okay, but then which linkage method you have to choose, so that totally depends on you. Okay, and there is no hard and fast rules as to which method has to be taken. Okay, you always select, I mean, you go for a method that will always give you the good results. Okay, so coming to agglomerative clustering, you can see here, I mean, an animation for agglomerative clustering. So where it stands, initially it starts with individual points in each data point, sample point in each cluster. Then the ones which are close by, the two samples which are close by starts getting merged. So the process continues till you land up with a single cluster. Okay, so that's what I just wanted to show you, how the agglomerative clustering happens. I hope you can see the animation. You're seeing the animation. Finally, you land up with a single cluster. So this is the final thing. Okay, so that's what is agglomerative clustering all about. Okay, so out here you can see something called a concept called dendrogram. Okay, dendrogram. Okay, so dendrogram, you can see, yeah, as shown here, it is like a tree like structure, a tree diagram, which shows the hierarchical relationship between different sets of data. Okay, actually this basically will record the sequence of how the merging is happening or how the split is happening. Okay, so or you can say this dendrogram is showing, it's basically a plot or a visual representation, which will show you the hierarchy of the clusters. Okay, so actually to get the number of clusters for hierarchical clustering, we make use of this awesome concept called dendrogram. Okay, so where you decompose the data objects into several levels of nested partitioning, trees or clusters called a dendrogram. Okay, so that's what is the concept of dendrograms. Okay, we are not going in detail to it. Okay, what I mean, how do we construct and other things, because it's just mentioned as a small topic, one, density based clustering. Okay, I'm just showing you the various, just briefing you the various algorithms involved. Okay, so you can see here, this is a dendrogram representation for a hierarchical clustering dendrogram. Okay, so initially if you see, this is its proceeding, let's let it start. So you can see initially this p5 and p6, p5 and p6, they are close. This now, okay, now it's close, and they are getting merged, they are getting combined. Then the next step, they get combined with p4. That's how the cluster c2 forms. You can see here red color, c2. Then after that, the next step is at blue one is, that is p1 is getting combined with P2, P1 and P2 gets combined because it goes very fast. Okay, you can just see it in multiple rounds. Okay, the next step is after the red, it's the blue. The P1 and P2 gets combined into one cluster, followed by your P naught. This one, P naught. Okay, so they get combined into one cluster. So I think that is being mentioned as blue color cluster is, I think, C4. Let me check. Yeah. So then the P3, P3 gets merged in cluster C2, and finally everything gets converged into one. Okay. So that's what is your hierarchical clustering all about. I mean, agglomerative clustering all about. Okay. So next we have this technique called divisive analysis, which is the opposite of agglomerative clustering. Okay, so this is actually called a top-down approach. Okay, so top-down approach. Okay, top-down approach means you start with the single big cluster where all the data points are in one single cluster. Then you start dividing it opposite of your agglomerative clustering. Okay, so here a single cluster of all samples of the data set taken initially. Okay, then it starts getting partitioned. Okay, so the partitioning process will continue till each data point lands up in a single sample. Okay, so that's what it's the inverse order of your Agnes, agglomerative clustering. So eventually each node forms a cluster of its own. Just a second. One second, I'm not able to write. Okay, fine. That's the main issue when I put a slideshow. Okay, right. So we were discussing about divisive clustering. Okay, so divisive clustering, top-down approach. So you assign all the observations to a single cluster, and then you start partitioning the cluster to two least similar clusters, and then you proceed recursively until you have one cluster with each one observation, one cluster in one one cluster in one data point in one cluster. Okay, so this is exactly the opposite of your agglomerative clustering. But then in actual real world, this divisive clustering technique is not much useful. Not much useful in the real world. Okay, so yeah. Now coming to the distance between the clusters. So I said in agglomerative clusters, the distance we went for a single link method. Okay, so just like single link method, I had mentioned that there are several ways to measure the distance between the clusters. Okay, so in order to decide the rules of clustering, okay, and that's what is called the linkage method. So these are the linkage methods. You have 1, 2, 3, 4, 5 linkage methods. Okay, so rather than just the definitions are being given out here. Okay, so how it is. Okay, so when you say single linkage, I had already told you the distance, the shortest distance between the 2 points in each cluster, that's what is called the single linkage. Then we have the complete linkage. Okay, that is opposite of single linkage, that is the longest distance between 2 points in each cluster. So that's what is complete linkage. Okay, the longest distance between each point, the longest distance between the 2 points in each cluster, that's what is called the complete linkage. Okay, then of course you have what is called average linkage. Okay, average linkage means the mean distance, average distance between each point in one cluster. You can see here average distance between each point in one cluster to every other point in the second cluster. Okay, so that's what is called average linkage. Then of course you have your centroid and medoid, about which you are very familiar when we discussed your K-means clustering and all. Okay, so centroid linkage means you find the centroid of one particular cluster, let's say cluster 1, and a centroid of cluster 2, and then you calculate the distance between those two before merging them. That's what is called a centroid. Okay, so then again you have this medoid also. Okay, a centrally located object in the cluster. Okay, that's a little more representative distance way of expressing the distance between the cluster. That's what is called medoid. Okay, so then as I said, though there are many techniques which will tell you, though there are many linkage methods, there is no hard and fast rule which one will give you the good result, or which is the better and which is the, I mean, good best one. Okay, so different linkage methods will lead to different clusters. So that's a summary which I wanted to tell you. Okay, so that's regarding your two types of hierarchical clustering. One is what is called your agglomerative clustering, Agnes. You start with a single point, start merging the nearest data points, and then finally you land up with a single cluster, which is called a bottom-up approach. The second one is what is called the divisive clustering, top-down approach, where you start with the entire data set as a single cluster, then you start partitioning the least similar ones, and finally you land up with one sample in one cluster. That's the top-down approach. Okay, then also we looked into the distance map, the different linkage methods also. Okay, so these are the various equations and other things for it, the centroid, the radius, the diameter, and other things. Okay, so if you see this hierarchical clustering, the main disadvantage of this particular approach is that, okay, so once the cluster is being formed, okay, it's a sort of irreversible decision. So that's what is being mentioned here, can never undo what was done previously. Okay, so it is an irreversible decision. Okay, so and it doesn't scale well also. Okay, then of course we have some more techniques, which is a hybrid technique, an integration of hierarchical and distance-based clustering. You have two techniques. One is what is called Birch technique, and second one is what is called chameleon technique. Heard of what is in? Have you heard of chameleon? Heard of chameleon? The animal called a chameleon.
Yes, ma'am.
Okay. Something which changes its color depending upon the surrounding. Okay, so now what I want to tell you is, if you look into your syllabus, I'll just project the syllabus here. Can you see it? Are you able to see it? Yes or no, please?
Yes, ma'am.
Okay, so I just mentioned there are two techniques. There are two hybrid techniques called Birch technique and chameleon, but then only Birch is being mentioned in your syllabus. So I will be doing only this Birch technique. Okay, so we are here right now. We have discussed cluster analysis, requirements, partitioning techniques, k-means, k-medoids, and one more Clarence. Then we started with hybrid hierarchical method, agglomerative versus divisive, what we just did. Then the distance measures in a algorithmic methods. That's what linkage methods we discussed. Next, we are going to discuss what is called the Birch technique. After that, chameleon I will not be discussing. In case time permits, maybe later as an extra thing we can discuss. Otherwise, after the Birch technique, we will move on to the density-based technique. Okay, so in that also, I will be discussing only the ones which is being mentioned in the syllabus due to lack of time and other things. Okay, so that's what I just wanted to show you. Okay, so the next what we are going to discuss is Birch, BIRCH. Okay, so let's see what it stands for. Okay, so please make a note. I feel all of you are sleeping. Birch stands for balanced, iterative, reducing, and clustering using hierarchies. The full form for Birch. Okay, so yeah, so what it stands for. Okay, so the clustering algorithm, like k-means, what we have studied. Okay, so they do not perform clustering very efficiently when it comes to large data sets. Okay, and it's difficult to process large data set with limited amount of resources like memory, or when you have slower CPU and other things. So k-means falls short with when it comes to all these aspects. Okay, so the regular clustering algorithm like your k-means or k-medoids or whatever, they do not scale well in terms of running time and quality as the size of the data set increases, because these days we speak all about VLD, very large data sets and very large databases. Okay, so it is at this point of time your Birch algorithm pitches in. Okay, so it's suitable for, it'll take care of all these aspects, the performance aspects and the size of the data set. Okay, it's suitable for all these things. Okay, so you can see in the PPT, balanced, iterative, reducing, and clustering. It uses hierarchies. Using hierarchies is a clustering algorithm that can cluster large data sets by first generating a small and compact summary of the large data set that retains as much information as possible. Okay, so this smaller summary is then clustered instead of clustering the larger data set. Okay, so you can look into the technique which is being followed by Birch. Okay, so it's basically what it do is it will first generate a summary, a compact summary of the large data set that retains as much as information as possible, and that smaller, the subset data set is being clustered rather than clustering the larger data set. Okay, so this Birch is actually often used to complement other clustering algorithms because it creates this summary data set. Okay, and the other clustering algorithms can make use of that representative set, okay, for further analysis. Okay, so that's what your Birch is all about. Okay, so so these are some additional features. Yeah, before we start with the phase 1 and phase 2, the point to be noted is you can see here it's mentioned a weakness associated with the Birch. Okay, Birch algorithm. It handles only numeric data and sensitive to the order of the data record. Okay, so it means it can handle only metric attributes. Okay, so metric attributes means the attributes which can be represented in the so-called Euclidean space, because it will not be able to take care of what is called their categorical attributes. Okay, it should be numeric data. It should be numeric data or metric attribute. Okay, and that's one weakness which is associated with Birch. Okay, so but then this particular algorithm scales linearly. It finds a good clustering with a single scan. Okay, so that's the fact which is very appreciable as far as Birch algorithm is concerned. Okay, so in most of the cases, Birch algorithm only requires a single scan of the database. Okay, so finds a good clustering with a single scan and improves the quality with few additional scans. That is quality improvement. Otherwise, Birch requires only a single scan of the database. Okay, so now let's move on into Birch little more in detail. What is this all about? Okay, so when you say Birch, so Birch has the two, if you see, if I tell you what the objective of this Birch is, there are two objectives for Birch. So one is hierarchical clustering, along with that iterative partitioning. Okay, so these two are the objectives of your Birch algorithm: hierarchical clustering and iterative partitioning. Okay, so before we start with this phase 1 and phase 2 and let myself telling you what this is all about, we need to understand two important terminologies associated with Birch. Okay, so one is what is called your clustering feature or CF, and the second one is what is called the CF tree, clustering feature tree. Okay, the first aspect is clustering feature and the second aspect is clustering feature tree. Are you all listening? Srikanth, listening? No one is listening, is it?
Listening, ma'am.
Listening, huh? Okay. I feel miserable handling class like this. Okay, so these are the two important terms. These are interesting things. Please listen. So first one is, let's see what this clustering feature is all about. And second, let's see what this clustering featuring tree is all about. Okay, so let's start with the first one, clustering feature. Okay, so when we say clustering feature, it's basically a three-dimensional vector. You can see here, 1, 2, 3, with 3 elements. Okay, a three-dimensional vector. Okay, so this n is actually the number of data points in the cluster. Okay, so that is number of points in the cluster. Okay, so then ls. Okay, ls is actually the linear sum of data points. The linear sum of the data, n data points. That's what is being mentioned here in this equation, sigma xi I equal to 1 to n. Okay, then you have SS. SS is nothing but this squared sum of the data points in the cluster. Okay, that is sigma xi square. Okay, so it is nothing but a three-dimensional vector. Okay, so an example is being given here. Okay, an example is being given here. Okay, so this you can say these. Let's say these are the 5 points being given to you: 3, 4, 2, 6, 4, 5, 4, 7, and 3, 8. Okay, so can you compute the clustering feature for these 5 points? Clustering feature vector in Birch for these 5 points. So this is the answer given to you. How do you get this? How do you get this? What is this value? What is this value? 5. Come on. What is this value 5? What is the first point or the first element in your three-dimensional vector? N is the number of data points. How is n 5 here? You have 5 points here, right? 1, 2, 3, 4, 5. So that's the reason why we have 5 here. Okay, this is the first one, n. Okay, so next is LS. LS is nothing but linear sum of n points. Can somebody find smart enough to tell me how you get this value 16, 30 here? Give a try. Linear sum of n points, sigma xi. I'm getting the answer as 16, 30. How is that?
Sum all x coordinate and y coordinate.
Yes, very good. So 3 plus 2 plus 4 plus 4 plus 3 will give you 16. Okay, then I'll write it here if you want. 3 plus 2 plus 4 plus 4 plus 3. So that gives you 16. Okay, so same way your y coordinates 4 plus 6 plus 5 plus 7 plus 8 will give you the value 30. That is this linear sum, LS. Then what about this 54, 190, Rakesh? This is SS. How do you get this value, Rakesh? People are thinking, madam is asking wrong question early in the morning to irritate people. Correct, no, Santosh? How do you get this SS? Square sum of n points. If you can get LS, what is the big deal in getting SS? Sharon, how do you get this SS? Sharon Varghese.
Square of the x, square of sum of x values. And
that's it. 3 square plus 2 square plus 4 square plus 4 square plus 3 square will give you 54. And again, 4 square plus 6 square plus 5 square plus 7 square plus 8 square will give you 190. That's what. Okay, so that's what this featuring vector is all about. Okay, so I hope it's clear what this featuring vector is all about, a three-dimensional vector. Okay, so it which has got 3 elements. First one is the number of data points, second one is the linear sum, and the third one is the square sum of n points. Okay, so this feature vector, clustering feature vector, so statistically we can call it as, you can say, you have this 3 things, no? N, S, LS, and SS. Okay, N can be called as the 0th moment of a cluster. Okay, then LS can be called as the first moment of a cluster. Then SS can be considered as second moment of a cluster. That is actually from a statistical point of view. Okay, we are calling it as 0th moment of a cluster, nth moment of a cluster, sorry, first moment of a cluster, and second moment of a cluster. Okay, so that's what your clustering feature vector is all about. Okay, it registers crucial measurements for computing the cluster and utilizes the storage efficiently. Okay, I hope you have understood what the first terminology is all about. Any doubts? Clustering feature. You people don't have doubts. Only I get doubts regarding whether you have doubts. Am I right? I hope it's clear. Clustering features. Okay, so now let's move on to the next one. The next one is what is called a CF tree, clustering feature tree. Okay, the second one, CF tree. Okay, right. So when you say this clustering feature tree, you can, I mean, think of it as a height balanced tree. Okay, for storing the clustering feature. Let me show you. Okay, a height balanced tree, which will store the clustering feature. Okay, so you can see here CF1, CF2, CF3, and other things. The child and the leaf node. These are all the non-leaf nodes. Then you have the leaf node out here. Okay, so from the set of data points, from the data set what we have. Okay, so what we basically do is we will compute the CF vector, that is the clustering feature vector, and then we will construct the clustering feature tree. Okay, so that's what we basically do in Birch algorithm. Okay, so we first compute the clustering feature vector. We know how to compute the clustering feature vector, what it is, a three-dimensional thing. It will show you the statistical summary and other things, the zeroth, first, and the second momentum. All those things I told you, and what the purpose of it also I told you. Then now I said the CF tree, the clustering feature tree, you can imagine to be a height balanced tree, okay, which will store the clustering features. Okay, so we will first compute the CF vector and then we will construct the CF tree. Okay, so this particular CF tree will have two parameters. Okay, the CF tree has got two parameters. The first one is what is called the branching factor, and the second one is what is called the threshold value. Okay, so branching factor and the threshold value. So branching factor means, as mentioned here, the maximum number of children per non-leaf node. Okay, per non-leaf node, how many number of maximum number of children, that is what is called the branching factor. Okay, then we have what is called a threshold. Threshold means the maximum diameter of the subclusters stored at the leaf node of the tree. Okay, leaf node of the tree. So basically this CF tree, maybe you can say it's you would have learned in your data structures or in your DAA called something called a B plus tree. Have you learned? Nobody will respond. Okay, of course you have learned. I myself will assume. Okay, so CF tree is basically a B plus tree. Okay, so we need to look at only the leaf nodes. Okay, we need to look at only the leaf nodes. Okay, so that's where your data values are. Okay, so this CF tree, this clustering feature tree, it's similar to a B plus tree. Okay, so in this Birch algorithm, you have basically two phases. Okay, two phases. The first phase, what you basically do is you scan the database to build the initial CF tree. Okay, so you scan the database to build the initial CF tree, and in phase 2, you apply a clustering algorithm to cluster the leaf nodes of the CF tree. Okay, so if you ask me why we are doing this, of course, the main advantage of doing this is, okay, so what are all the, dense clusters, okay, all the dense data points, they all will get grouped as a larger cluster, whereas all the sparse clusters which are scattered here and there, so they can be removed as a outlier. Okay, so that's the main advantage of doing this. Okay, so that is remove sparse clusters as outliers and group dense clusters to larger ones. Okay, so that's the main advantage of this. Okay, so now if you look into the CF tree, okay, this is the two phases which we are right now looking into, phase 1 and phase 2. Okay, so now if you look into this CF tree, clustering feature tree, so this CF tree is actually dynamically built as the objects are getting inserted. Okay, so objects will get inserted into the closest leaf entry, just like your B plus tree. Okay, so the leaf node will be the cluster. You can see here the cluster. The leaf node will be the cluster. Okay, so if the diameter of the subcluster stored in the leaf node after the insertion, if it's larger than the threshold value, then that leaf node and maybe probably the other nodes will also start getting splitted. Okay, so when you say the size of the CF tree, that is actually determined by the threshold value. You have something called a threshold value here, right? So the maximum diameter or something. Okay, so if the diameter of the subcluster, whatever is stored in the leaf node after insertion, if it is larger than this particular threshold value, that time a split will happen. Okay, so the size is determined by the threshold value. Okay, so how this insertion of the node happens, how the splitting happens, everything is same. I mean, how the insertion and node splitting happens in B plus tree, the same way it happens in Birch algorithm. I'm not going to illustrate this or anything. Okay, so I mean, only so much I'm going to tell you. Okay, how it happens. Okay, so because it's a combination hybrid technique. Okay, so how the insertion and node splitting happens in the B plus tree, the same way it happens as far as the Birch algorithm is concerned. Okay, so now if you look into the complexity of this, the complexity of the Birch algorithm, it is of the order O of n, where n is the number of objects to be clustered. Okay, n is the number of objects to be clustered. Okay, so it is the major concerns are it's sensitive to the insertion order of the data points. Since we fix the size of the leaf node, clusters may not be so natural. Okay, then clusters tend to be spherical given the radius and the diameter measures. Okay, so this is the thing what I just told you regarding what basically happens in the CF tree. CF tree is being dynamically built as the objects are getting inserted. Okay, so objects get inserted into the closest leaf entry, just like your B plus tree. Okay, so the leaf node will be the cluster. Okay, so in case the diameter is greater than larger than the threshold value, the case, see, you can see here diameter greater than the maximum diameter, then the leaf will be split, and possibly the parents, that is associated nodes, also will get split. Okay, so the size is determined by the threshold value, and how the insertion, splitting, everything happens, it's the same as how it happens in B plus tree. The same thing happens here in Birch algorithm also. Okay, so that's what your Birch algorithm is all about. Okay, so okay, so this is one of the important integration technique, hybrid technique, which combines hierarchical and distance-based clustering. So Birch, okay, how Birch does. Okay, so what are the two important terminologies associated with it? Clustering feature vector. I told you what is a clustering feature vector and other things. Then what this CF tree is all about. Okay, the two parameters for it. Okay, then it looks like a B plus tree, what it is, how things happen in a CF tree. Then what you basically do, you scan the database, you build the initial CF tree, then you apply a clustering algorithm to cluster the leaf nodes of the CF tree, and how things happen here, and what are the major concerns, and what is the complexity of this particular algorithm. Okay, so that's what your hierarchical clustering algorithm is all about. Okay, so can somebody at least list me the three techniques that we have discussed in hierarchical clustering? The three techniques. What are the three techniques we discussed in hierarchical clustering today?
Agnes, Diana, and lastly
Yes,
Birch.
Agnes, agglomerative clustering, divisive clustering, Diana, and a hybrid technique called Birch. Of course, we do have chameleon, but then I'm going strictly as per your syllabus because we are at the fag end of the semester. So we are here, we completed the Birch. So next we move on to what is called DB-scan technique, which is nothing but density-based clustering technique. So before we start with that, let me quickly take the attendance and then start. Answer your attendance. Anirudh?
Present, ma'am.
Dharini? Ramharini?
Present, ma'am.
Kalyan Sundar?
Present, ma'am.
Aravind?
Present, ma'am.
Aravind.
Present, ma'am.
Aravind, okay. Everybody are getting up with the attendance. Sharan Varghese is there. Okay. Shakti Priya. Nishok.
Present, ma'am.
Priya.
Present, ma'am.
Likita. 27 Likita. No response. A marker is absent. Suveda.
Present, ma'am.
So it is Suveda who told me the attendance now, right? Likita is absent.
27 present, ma'am.
27 is present. Okay.
30 present, ma'am.
30 also present. Noted. Fine. Vishal Bhashyam.
Present, ma'am.
M. Srimati.
Present, ma'am.
Nityashri.
Yes, ma'am.
Pranavram.
Present, ma'am.
Srimati S.
Present, ma'am.
Raja Singh.
Present, ma'am.
Pooja.
Yes, ma'am.
Lavanya.
Present, ma'am.
Nityashri.
Present, ma'am.
Sriram.
Present, ma'am.
Satyamohan.
Present, ma'am.
Karan.
Present, ma'am.
Aviral Patel.
Present, ma'am.
Was it interesting, Aviral, or boring?
Ma'am, it was very interesting, ma'am.
Wow.
I like DMA, ma'am.
Okay. At least one good feedback from the class. Thank you. Hemavartini.
Present, ma'am.
Ajay.
Ajay, present, ma'am.
Akshita Saha. Okay.
Akshata chat box, ma'am.
Noted. Karthik Balaji.
Present, ma'am.
Santosh Kumar.
Yes, ma'am.
Anandarun. Okay, noted. Rahul P. Noted. Suhasini Shrikant.
Present, ma'am.
People are giving attendance and leaving. Why is that? I'm going to start with the next technique, density-based technique. Don't start, leave. Another 5 more minutes are there. Okay, Suhasini Shrikant, fine. Apurva Ravichandran.
Present, ma'am.
Vitun.
Present, ma'am.
Adityan.
Present, ma'am.
Selva Niklesh.
Present, ma'am.
Ramcharan.
Present, ma'am.
Pinta Murari is texted here. Okay, noted. Santosh Kumar.
Present, ma'am.
Pavitra Shri.
Present, ma'am.
Praveen.
Present, ma'am.
Rakesh.
Present, ma'am.
Oof. So your mic don't have any issue, right? Only when I ask question it creates issues. Is it, Rakesh?
Ma'am, now the network is clear, ma'am.
Network is clear. Yes. While attendance network is very, very clear. Nityashri Narasimhan. 1 from C section. 001. No response. Nishok Atiraven.
Present, ma'am.
Abel Prashant.
Present, ma'am.
Deepika.
Present, ma'am.
Kevin Kurian Joseph.
Present, ma'am.
Kitain.
Present, ma'am.
Adya.
Present, ma'am.
Devora. No response. Absent.
Ma'am, can you hear me now, ma'am?
Oh, is that Devora? Okay. Kishore.
Present, ma'am.
Sridevi.
Present, ma'am.
Yash Rai.
Yes, ma'am.
Jayesh Kumar.
Present, ma'am.
Okay. So as per the attendance, only Nityashri Narasimhan is absent from C section. But as per the meet, only 44 are there. Okay, 2 more minutes are there. I'm starting with the next topic because we are running short of time. Okay, so we have discussed partitioning techniques. We have discussed hierarchical techniques. Okay, so next we move on to what is called density-based techniques. 2 minutes, we'll discuss density-based techniques and then you can move on to the next class. Okay, 3rd and 4th hour is cancelled, so you can be happy, you can enjoy. Okay, so density-based clustering technique. Okay, actually, you have 3 algorithms, 3 techniques. There are 4 techniques, in fact. So the popular ones are DBScan, optics, and DENCLU. Click, though it is being put here, it is more of a grid-based technique. It's more of a grid-based technique. With grid-based techniques, finally, the next section we will be discussing about grid-based techniques. Okay, so this among these various algorithms, we will be discussing only about DBScan. Okay, optics and DENCLU is not being mentioned in your syllabus, so we will not be discussing that. You can see here. So after DBScan, I'll be straight away discussing 2 grid-based techniques. One is Sting and one is Click. Okay, so sting and click will be discussed, and DB scan from density based clustering technique. We go by the syllabus. Okay, so this DB scan is actually a different type of clustering algorithm with some unique advantages. Okay, so here from the name itself, you can hear it is called density based. Okay, so this method basically focuses more on the proximity and the density of the observations when you form the cluster. Okay, so this is actually very different from k-means. Okay, so k-means means an observation will become a part of the cluster which is being represented by the nearest centroid. But then this DB scan, it's capable of identifying the outliers, the observations which do not belong to the class category. Okay, and again they are capable of finding out, discovering spherical shaped clusters, whereas your arbitrary shaped clusters, your k-means can identify only spherical shaped clusters, whereas your density based clustering techniques like DB scan, it can discover clusters of arbitrary shape, non-convex shapes and other things. So that's the main feature of this density based clustering. Okay, so with that I'm stopping. The strength itself is 39, and it's time for the next class. Thank you. No thank you from the class. Okay.